All right. Hello, all. All right. So that's slow. Sorry, it's already 7:30, man. That segment ran long. I didn't think it was gonna run as long as it did, but um okay, so this week we're doing network shortest path, I think. Let me grab it. Network delay time. All right. I'm curious, have any of you tried it? Have any of you attempted this one?
Nope.
No? Okay.
Not at all.
Okay.
Probably law. Like, oh boy.
So, all right, we're gonna do the read through and then we're gonna sort of talk because I'm gonna be honest with you. There's a decent amount of theory I have to walk through with this one. So I don't know. Um I actually did something a little different this time. I threw the solution up in the technical thing already because I have a feeling we may just like walk through the code. Like by the time we get to it, because it's already 7:35 and
That's perfect.
by the time we might do this week a little bit differently because I'm going to recognize we've got to do some stuff. Okay, so network delay time. So okay, got pulled up. Cool. You are given a network of n nodes labeled from 1 to n, right? So you have all these nodes here, 1 to n. And you're also given times, a list of travel times as directed edges. So times, you're going to notice here you have a list of times here, which is composed of a source node, a target node. So U is source, V is target, and W is the time. And that's like the least useful alphabet letters you could have used for that. Um, but so basically it's sort of and so W is the time it takes for the signal to travel from a source to target. So by the way, this is what we call a weighted graph. So taking a step back, so we've already had this idea that you have graphs, which is you have a series of nodes and then you have edges or which is sort of paths between the nodes. And we've sort of done traversals, depth first, breadth search. And up to this point, we've sort of had a uniform cost assumption, which said there's an equal cost to traverse every node. Now, of course, in real life, that obviously is not typically the case. And in fact, there's more often than not, actually thinking about it as a weighted graph makes a lot more sense. So, classic example, if you want to get from point A to point Z, and right, you think about like the Google Maps, and I'll show you the different routes you can take. There's a bunch of, and you imagine each place being different nodes, and there's pathways. Well, there's different, there's distances, there's speed limits, right? There's costs to traverse from point A to point B. And so that's what a weighted graph is. A weighted graph says that these edges, these lines that connect these nodes, don't necessarily have a uniform cost. In this example, they do, but imagine that they have different costs. And so, oh yeah, cost is a number. It's the way. So you'll notice how there's like a 1, 1, 1 here. So that's sort of the cost to travel from node 2 to node 3. And again, maybe an easy way to think about this is you could think about like distance. Like it's 1 mile to go from node 2 to node 1, but maybe it's 10 miles to go from node 2 to node 3. Something like that. Um, or, yeah. And so, right. So the idea is, again, whether it's distance or some other sort of metric, but the idea is that just because there's a route between them, just because these two are connected, doesn't mean there's a uniform sort of cost to make that traversal.
Would this be like an application like GPS?
Absolutely. Yes. So absolutely. So GPS shortest path, Google Maps is basically like a classic version of this. Hi, I want to go to Santa Monica from here. Shortest path, right? So exactly. It's yes. So that is classic. But we use this for a lot of things. We use it for the network questions. We use these for, if you have a bunch, and this is what we're looking at here, for instance. So you have you have in this case like a sequence of servers, and that is sort of you have a message that's propagating, and it's sort of how long, and this is fundamentally what it's going to ask. So actually, sorry, let me actually keep reading this. But so let me start from the beginning, right? You have a network of nodes, and again, you can think of it as servers or locations or things like that. and we label it from 1 to n. You also times, and that's travel times for these directed edges. So again, and this is represented this way. You have your source node, your target node. So like for instance here, there's a directed edge, which means it goes from 2 to 1, right? And sometimes these are bidirectional, where they can go both ways. In this case, directed means it only goes one way. So in this case, source, terminus, time, or cost, right? And that is the amount of time it takes for the signal to travel from the source to the target. So it says we will send a signal from a given node K. And so it says return the minimum time it's going to take for all nodes to receive the signal. So you have a connected graph. You have a single node here that's your source node, and you want to see what the minimum amount of time it's going to take for a signal to propagate through the entire network. Oh, wait a second. Wait, I have a thumb. Do I have a hands up? Oh, that's funny. I literally. Wait, how do I put my? No, I don't want that. Okay, can it go away? How do I deactivate that? I don't want that. Bollocks. Okay, well now I can't make it go away. How do I make it go away? That's annoying. Go. No? Okay. All right, let me look. All right, and I'm gonna pause the recording so it doesn't like 5 minutes of me looking how to make my little hand emoji go away. Okay, so as an example here, if your K, so this first input here, if your K is 2, which means your starting node, the output's going to be 2. Why? Because you'll notice at time t of 1, it'll traverse to 1 and 3. At time t of 2, it will traverse to 4. All right. So, okay, so that's the general idea. So, oh, wait a second. Can I? No, that didn't get rid of it. Okay. Yeah, and by the way, sorry, guys, for those of you on the recording, we have no idea how to get my hand to go down. I don't have reactions. Wait, Era, you have reactions. Wait, I can lower your hand. I literally have a dialogue to lower your hand.
Yeah.
I just can't lower mine. Okay. Yeah. All right. So anyway, it's there. We tried to debug it. We're not wasting any more time. It's just that.
Try making someone else host, and then they might be able to lower your hand.
Oh, okay. Who wants to be host? Okay. Hang
Make
on.
me host. That's fine.
Okay, it was your idea. So, Kurt, I'm making you co-host. All right. Are you able to lower my hand?
Let's see.
If you mouse over me in the participants pane?
No, I cannot.
Interesting. Okay. Yeah, all right.
Since they're co-hosts, they can't.
Can't override me.
Yeah.
Thing is, I don't want to make you host, Kern, just because I'm recording this and I don't
Oh,
know
okay, yeah, that's fine.
what happens if
Anyway,
anyway. Okay. It is what it is. Okay, so background on this. Frankly, I don't even know how to begin to solve this without Dijkstra. Maybe you guys have some ideas, but this is just Dijkstra. Oh wait, did I not make? Oh, Kern, I may not. Ooh,
oh, okay. Now I see stuff.
hang on.
Host tools.
Wait. Oh, I lost the meeting now.
Uh-oh.
Bollocks. Hang on. I'm going back to the meeting. Am I in the meeting now? Oh yeah, I'm back. Okay. Okay. Is my hand down?
No, your hand's not.
Oh. Oh. Whatever.
Do you have the react button now?
Let's see.
Oh, there we go.
Can you put my hand? Oh. So you were able to lower it for me?
Yep. Yep.
Okay, but I'm not gonna. I'm gonna like keep my hands like this now. Like, no, like, can't get over expressive. I've learned my lesson. All right, so let's talk Dijkstra's. Okay. So this is kind of cool because in this class we have talked about greedy. Remember greedy? Feels like a lifetime ago. To talk about greedy, right? Greedy algorithms was this idea that you can basically, you iteratively, you don't sort of exhaustively look at every possible permutation. You figure out a pattern and you just kind of run through your thing. And every time you're sort of making your best guess estimate. And the idea is that at every step you're making the optimal choice. So your algorithm never falls behind. And so that when you are done, you have essentially, right, you've arrived at the optimal solution. That was greedy. And then we looked at graph traversals. So we looked at breadth first search when we did islands, yeah. Island, number of islands, right? And that was the idea of just this tree that expands out and we iteratively search every row. And if you remember, that was a queue-based thing, right? First in, first out approach. And then last week, when we were looking at word search, we did depth first search. Depth first, again, you're still traversing, but you're sort of just randomly following a path until you hit a dead end, then you backtrack, you try something else, backtrack. And that's a definition of a stack, right? Last in, first out was sort of the approach for that. But one of the underlying assumptions that sort of governed both of those traversals is the idea that all of those edges have equal weights. Right? In fact, we didn't even talk about that. That wasn't even something that we like conceived of, because in our mind, all edges were equal. So it was just a question of what order you traverse them, because there was really no reason to choose one over the other. And really, it was just a question of making sure you did it systematically, right? So it was whether, one approach that you just need to make sure you were thorough and exhaustive, because fundamentally it was all the same. And so comprehensiveness was the key. But what if now we're introducing the idea of graphs having weighted edges, right? And where we may try to minimize the total cost to traverse our graph. So now suddenly edge selection is not arbitrary, right? Because there is a cost depending on which edge we choose. So tying these two ideas together, is there an approach we might consider taking to deciding what edge we choose? What do you guys think?
Is there what?
Is there a strategy we might employ to choosing what edge we choose?
Would it be kind of like a combination of that first search with like greedy, where it's like, oh, if left side is more, no, sorry. If we're doing greedy, it'll be like, if right side is more, we're gonna move it to the left. So they're both on the same point, and then we'll return the lowest number.
Yeah, good. So I think you're sort of thinking along these lines, but the idea being, right, in breadth first, you're choosing it based on first in, first out, right? You're choosing whatever you've encountered first. Depth, you're choosing whatever you happen to have encountered last.
Okay.
Greedy approach says, choose the lowest cost one, right? Always choose the edge that has the lowest cost and traverse that. And then keep traversing that until, and this is, I think, to your point, until it becomes too, like, if you're comparing your outcomes, until the cost to go this way, like you keep going this way, until the cost is greater to go this way, continue this way, then go this way, and then you go this way, right? That's the general idea. And yes, that intuition of saying, let's greedily traverse the graph based on lowest cumulative cost is precisely what Dijkstra's is. Like that is Dijkstra's in a nutshell. So yeah, so again, your greedy approach to this is, rather than doing it arbitrarily or systematically, always choose the path with the cumulatively smallest cost. And then at every iteration, every time you choose the edge that has the lowest cumulative cost, you recalculate, and then you decide whether or not to keep on the current branch, extend one more, or pivot to another branch, because now the cost is less, right? So when you continue going along that road until the lowest path is reached. Okay. So I think this is going to be helpful for us to do this, is sort of walk through what this looks like. So let's actually sort of walk through Dijkstra. So we have here a thing, and again, similar to our problem, we want to know what the minimum cost is going to be to traverse every node in this graph. Okay, so that's going to be our goal here. And in this case, our starting node is going to be here. Why? Oh, it can be arbitrary. Yeah, it just happens. No, good question. There's nothing meaningful. It's just we just happen to originate there. We could originate theoretically from anywhere, and the graph would run.
In last week's lecture for the data structure, Professor, he defined the top of the node as the one that does not have an edge. So like you could start out any of the nodes, but they cannot have an edge on top.
Okay, yeah, or yes, or another way of thinking about it is you cannot have an inbound node. Yes, it only has outbound nodes. So yeah, so I think yes, so that's fair. Yes. In this case, because this is bidirectional, theoretically, so theoretically, right, because it's not a directed graph, so you could theoretically start at any point. But
we're talking about trees.
yeah, but that is a good definition in general. A good place to start if you're looking for that is a node without any incoming edges. Yes, that's a fair definition. Yeah. Okay. So in this case, so here's, and by the way, these, and I want to visualize this and walk through this because this is ultimately going to be the steps that we're going to implement for our algorithm. This is where we're going to get to. And this is why I'm saying like this is going to take forever. Like we haven't even touched any Python yet. And so yeah. And it's already 8 o'clock. So we start with, so we're going to start, so this is going to be our source node. And so you're going to notice here, so we start it, we initialize it. And you'll notice something happens here. So we start this and we initialize this value to be 0. Because here, right, this is our start node, so it doesn't cost us anything. This is where we're at. And then you will notice we initialize all of the weights of all of these nodes to be infinite. So the idea here is we start saying we haven't started our graph yet. We don't know how long it's going to take us to traverse any of these things. So for now, we're going to assume, right, we're going to start with saying the cost to get to any of these nodes is infinite. And not that it actually is infinite, but the idea is you start it that way because you're always going to be updating it down, right? The goal is as you traverse your graph, you're going to update these costs to your lowest cost. Okay, so then let's see sort of how that works. So in this case, so we start here at this graph and we expand out and we say, okay, there's this graph can traverse to 2 other nodes. We're going to see here, okay, we've encountered cost. So here the cost is 4 and here the cost is 4. So now we update because now the new lowest cost to get to these nodes is 4, right? So now, and then we try to sort of expand out again. So in this case, looking from here, we say, okay, well, in this case, is there any other node, can this expand out? Well, this has 1 edge here. This way would cost 6. 4 is still less. So this is lowest path. So we're not going to do an update now because it's more expensive to go this way than just to stay on this route. Okay, so now we're here, we sort of expand out this one here. We're going to see here, we know that the shortest path to here is 4, so we're going to lock in 4. We now here have 4 plus 3, that gives us 7. We can go 4 plus 6, that gives us 10, and 4 plus 1 gives us 5. So we can unlock these that way. Then we now unlock these again, and we say, okay, well, so from here, we can get 7 plus 2. That theoretically gives me a shorter path here, which would be 9. But 5 plus 3 gives me 8. And now 8 becomes, when we sort of expand out these, we sort of, and I'm jumping through ahead of these a little bit here. But you'll notice here, right, in this case, going that way is going to be the shortest. If we try to go up there, 7 plus 2, right, that's greater than 8. So we lock in at 8. And so in this case, so now we know the shortest path, and critically, we also know the total time it's going to take to traverse the entire graph, which is 8, right? Because this is the last node that's reached. We know the cumulative cost to get here is 8, so we know the total time to do so is 8. So what we've done here is essentially what we're going to program out in Python. But we're not quite there yet. Because there's one other thing we have to talk about, which is the data structure for this. And the data structure for this is something called a min heap.
Okay.
Now, yeah, I know. I'm sorry. For my data structures, folks, have you guys talked about min heaps?
No, not yet.
Okay, well, you all going to get into it. So part of, all right, do I not have, where's my min heap notes? Oh. Okay, well, I posted some min heap notes here because I don't actually have lecture notes on it. But I do have, where is, wait, did I not upload my, maybe, wait a second. I know I had, did I not? Shores, path extras. Oh, bollocks, did I not upload it? Hang on. File. Min heap, there. Could have sworn I had it. Okay, well, now it's in the tech interview prep. Okay, so we got to talk about the min heap because we really can't. So, a big part of these algorithms is really sort of thinking through the data structure around them. And this is something I don't think I really appreciated the first time around when I learned these things. But, right, the whole idea that, again, BFS built around the queue, DFS built around the stack. Well, Dijkstra's is built around the min heap. And so we sort of need to talk about the min heap because in order to implement Dijkstra's, we have to implement a min heap to do it. And you'll see why, because the basic logic of a min heap is ultimately what sort of allows us to do this. So what is a min heap? A min heap is essentially, it's a binary tree with two guarantees. The first is heap order. And by the way, there are different types of heaps. There are max heaps. And so there are, but so a min heap, the whole idea is that each parent is less than or equal to its children. That is the basic structural thing. And in general, the shape of the tree is complete, which means it's always filled in. There are no gaps. And generally the result, wait a second, where's my little graphics for us? Okay. Okay, good. So I do have. The result is that the smallest element is always at the root. So always, so min heap index position 0 will always be the smallest element of it. And the basic use case of it gives me the current minimum fast. And we're going to talk about why this structure is done, because it's actually a really, really fascinating, like you may ask, like, and this is something that I actually struggled with. I was like, why is the, like, what are we doing with these complicated, like, why are I storing data in binary tree form? Like, what, like, why? I'm going to tell you why, because it's so cool. But okay, so general idea, are you guys able to see this?
Yeah.
So the general idea is, so we have sort of a list of numbers here, right? So we have, as you can see, 13, 16, 31, 41, 51, 100, and 115. And so the basic idea, again, is that the parent node will always be less than or equal to the children node. And it's always a binary tree. So the smallest value, 13, is always a root node. And then its two children, 16 and 31, are always here. And then you push these down here and these right goes on that way. And so that's why this is always there. Now, here's an interesting thing, and this is something I want to sort of emphasize with this, and I'll come back to this. You may have noticed that for both stacks and queues, we basically just used lists in Python.
Mm-hmm.
And that's something I want to emphasize here. We talk about these as being unique data structures, but the reality is we're just using lists, Python lists. It's just the way the rules for the lists are going to be different, but we're using the same basic structure. The only difference between a stack and a queue was, did we pop the thing at the end, right? Did we pop left or did we pop right? That was really the only difference in terms of those two approaches. But other than that, right, it was just basically a list. And so the thing about a min heap is it's still being stored as a list. You still have these index positions, standard index positions with the associated values. Again, the only difference is the way we're thinking about it conceptually is as a binary tree. And these are the rules. So generally speaking, if a parent is index I, then the left child will be index position 2 times I plus 1. The right child would be 2 times I plus 2. So you can sort of see here, right? If this is index position 0, then the left child will be index position 1, right? 2 times 0 is 1, and then 2 times 0 is 2. So 0, 1, and 2, right? 0, 1, and 2, that gives you that. And so there's just these rules, but then fundamentally they're represented as an array. And so, and I'll get to why we do this in a moment, but before I get to that, I sort of need to talk a little bit about core operation for this. Inserts and removals. So inserts, so pushes. So what happens with a push? So when a push happens, you essentially append a new value right to the end. So whatever sort of the current end is of your sort of binary tree, you append it to the end. And then we do what's called bubbling it up. So we basically do sort of a direct comparison operation where we say, okay, are you less than your parent node? If you are, you bubble it up. Are you less than your parent node? Bubble it up. And you basically sort of keep doing that until you're no longer less than. And that, by the way, and this is the really cool thing, this is why heaps are so useful. Because if I try to insert something, normally, I theoretically have to do some kind of search thing where I have to go through all of them and say, okay, well, where does this fit in? Is it greater than or less than or everything like this? But the cool thing with this is I can insert any value and I don't have to compare the things here. I don't have to compare any of these nodes here. I just have to compare its immediate parent. Is it less than or greater than the parent? If it's less than, pop it. If it's greater than, keep it where it is. And go on to that. And because of that, you only have to do log n operations. And I haven't gotten into the why on this, but that's the general that's what makes this data structure so cool, is I can insert new values in an ordered way using only a fraction of the normal calculations I would if I'm dealing with like an ordered list. So inserts, again, you append it right at the end. You take the very last index position, you just stack it on right there, and then you bubble it up. You compare it to parent, until you find its location, and then you stop. Removal is you basically just kind of remove the top one. You pop off the top one, and then you just sort of compare the next two, and then you reorganize the binary tree around that. So you lob the top one off, you compare these two, whichever one becomes things, that becomes top, and then you basically rearrange it that way. So again, it becomes a much easier way to sort of quickly maintain lowest value, where you can sort of dynamically add and remove elements as you're doing that. And then the other thing is just a quick view thing. So getting back to heaps. So again, so Python uses a particular library for this called heapq. I'm not really sure why we call it heapq, but that just is. It's a built-in min-heap toolkit. So I don't think you have to do any imports for it or anything like that. What you essentially do is you manage a list. So you create this little heap and it's a list. And then you have within the heapq library, again, you can sort of do heapq, heap push, and that's where you insert X into your heap, and then it will automatically bubble it up to its proper place. So basically appends it and then bubbles it up to its proper location. And again, then you have the heapq head heap pop, which will then pop and return the smallest value. And then reset your heap, your min heap. So it removes the smallest value and returns it. And then you can obviously always look at the smallest one by just referencing heap 0, index position 0. So it's a list. It's just we have this heapq library that does these operations for us. So, okay, so bringing these all together. So why does Dijkstra's use min heaps? So Dijkstra's needs to repeatedly get the unvisited node with the smallest distance so far. Right? So it needs to sort of figure out, okay, what is the smallest, unvisited node? And so a min heap gives us a really easy way to do that, sort of an O of log n per extraction. So without a heap, we have to linearly scan every time to do it. That's inherently scalar. So this keeps Dijkstra's very fast and very scalable. So that's why when we think about Dijkstra, we think about min heaps, because you use a min heap, because a min heap, as you'll see, when we construct it, is constantly just pulling whatever again, our heap is going to be based on the lowest available edge that we haven't traversed. We're going to do that. And we're like, oh, okay, is this like, do we add this to our path or not? And then we pop it and then we do that. And so we're always taking the smallest one. And so that's the structured approach for it. Whew.
Yeah.
Okay. It's a lot of
Yeah.
a lot of things we have to do. So, all right. So let me pause and do a sanity check here because it is after 8. There's sort of 2 ways we can do this. Version number 1, I walk you through the code. We type it out together. Version number 2, we just take up the code, load it, and I just walk it through with you. What would you guys prefer? Because
Just being loaned up, but I don't care. I mean, like, if you would prefer to write the code yourself, just because I have no idea if this is gonna work. So.
Yeah, because we haven't got like heaps yet, like it's
Yeah.
gonna be for next week, for the data structure class.
Mhm.
So if you wanna just load the code.
Yeah.
Okay.
And just talk through it, because even now, like, I understand
Yeah.
the binary tree, but like I said,
Right.
we haven't even got the heap yet.
Yeah. Okay.
You won't know.
So let's because I want to be. I mean, these are dense topics. I just want to be fully like sympathetic, and it's a combination. It's the 1-2 punch of it's really complex, and it's really late too. And it's like, yeah, and we're like 2 hours into a lecture, and it's like I don't know if you guys want me to. Okay, so if you want the code, if you go, so I sort of suspect that was going to be the case. So
Yeah.
if you go into the technical things, you will notice actually have shortest path.py. If you grab that file here, this should give you the solution you need.
Oh, okay. No, it's okay. Got it.
So let me just see if I can paste it and the formatting doesn't get all messed up. Oh, it gets messed up. Bollocks. Okay, well, we can download it. All right, so if you download it and then let me open it. Okay. All right, well, since I have it here, I can sort of talk through this right here. Make this a little bigger. Okay, so right here, let me make sure this works first before I wax philosophical about it. All right, just paste that in there. Let me run. Okay, accepted. Let me submit. Okay, cool. All right. It works. All right, so let's take a look at this and let's kind of walk through what we're doing right here. Make it nice and big on the screen. All right, so this is what they sort of give us here. And so remember, they're giving us a list of times associated with things, and then they're giving us the total number of nodes and our starting node. Those are sort of the things that they're giving us. Okay, so the first thing that we're going to do, the first thing that we build before we build anything else, is we build what's known as an adjacency list. And this is a very common sort of thing when you're dealing with weighted graphs. So being familiar with like adjacency lists is going to be helpful. So essentially an adjacency list is going to be a dictionary where you have your key is going to be the node, and the value is going to be a dictionary of sort of essentially nodes that it can reach and the associated cost to reach it. So basically, so if you're thinking about this like practically, I can sort of say, okay, well, node 1, it can reach, let's say, node 2 and it costs 5. It can reach node 3 and it costs 4. It can reach node 7 and it costs 10. That's basically that's what an adjacency list is. It's a dictionary where the key is its current node And then the value is a list of all nodes and the associated costs. So that's what we're building here. So you're going to see here, so graph I for I in range 1 to n plus 1. Because we're basically, right, because we're sort of playing with nodes, total number of nodes, and we're starting with 1. So we actually have to sort of play around, because remember, usually it's exclusive of. So because we're starting with 1 and going to there, so it's going to be n plus 1. So we're essentially creating here a blank, a blank sort of dictionary. So for every node, we have a blank dictionary now. So it's a blank adjacency list. Then for all of them, so now we loop through and we say, okay, for all of these in times, because times gives us, and you may recall, they even tell us, times gives us, remember, U, V, and W. U is source, V is target, and W is time. So going back here, so graph U, which is, again, the index, right, the node. So our source, we're going to append to the list, because remember, the value is a list. We're going to append target and time. So we build this adjacency list, and then we loop through the list of lists of times, and then we sort of append them there. So now we have an adjacency list. We can, for every node in our graph, we can look up what nodes it can reach and the costs associated with reaching those nodes. Okay, so that's the first thing that we've built. Now we're going to build a distance array. So this is going to be sort of the next thing. So you may remember, and this is why I think going through the visual is helpful. This distance array, we need to keep track of the total of the minimum cost for each node up until this point. Right? So you may remember, like when we initialized it, we initialized all of our nodes to be infinite. So that's what the distance array is. A distance array is basically, it's going to be a list where each value is going to be correspond to the node, right? So distance is going to be, so you're going to have node 1, node 2, node 3, node 4, node 5, but what we're keeping track of here is the shortest path to those nodes. And so when we initialize it, just like in the visual, when we initialize it, we initialize everything to be infinite, right? Everything, this is infinite, this is infinite, this is infinite, this is infinite, this is infinite. Okay, those are the worst infinites ever, but it's late. So that's how from a data perspective, we're basically keeping track of this, right? So we start off, everything is infinite, and then as we're going to be going through and traversing, right, just like we're doing this visually, and updating these as we go along, we're going to do the exact same thing. So this is just the data structure by which we're going to use it. So you're going to notice here, infinitely is just, we're storing this variable here, and then you're going to notice distance is inf times n plus 1. So we're basically doing a casting operation. We're creating these number of nodes, and we're setting the value equal to infinite. And then you're going to notice for distance of k, which again is our starting node, our source node, we set equal to 0. So again, algorithmically, that's exactly what we just did here. We said, this is our source. This is where we're starting off. Right. Dude, isn't this visual helpful? Like I could not even imagine talking through this without the visual. But that's exactly what we did. So we've created this array of all these. Right now, they're all set to infinite. And this is 0. And again, remember, we have this now adjacency list that allows us to say, oh, from this node, we can reach these two, and it costs us this, each of these costs this much, right? So we have the data structures now to do this traversal. We haven't done the traversal, but we have the data structures to do it. Whew, okay. So now we're going to begin to build our min heap. And you may remember the min heap is going to be, ultimately, it's going to be it's going to be a list of tuples where it is the current, it's going to be the current cost when we encounter an edge, the current cost to reach that node and the cost to get to that node. Now, and here's sort of an important thing to know here. It's not going to be the current cost cumulative cost. This is something that was a little tricky for me to keep track of. The min heap isn't going to keep track of lowest cumulative cost. Lowest cumulative cost is stored here in dist. The min heap tracks all of your edges. So the min heap says, when I open this one, I'm going to say, oh, I have 2 edges to these nodes. I'm going to push these 2 edges into these 2 nodes. And then whichever edge happens to be the lowest, I traverse it first. And I'm going to say, okay, so in this case, they're equal, so it doesn't really matter, but I'm going to traverse this one first. So I traverse this one first, and then it does this. But maybe, maybe this is a better example right here. So this one, when I expand these, so I'm at this point. So my min heap is going to have 1 with a node to here, 6 with a node to here, 3 with a node to here. So my min heap, when I bubble it up, this is going to be top of the heap. This is going to be next. This is going to be next. Which means I first explore this one. And then I add this one to the list, and I explore that one, and explore that one, and explore that one. So the idea is I'm always exploring the lowest edge available to me at a given time. So just, again, tricky to sort of keep in mind, but that's what this is going to be looking at. So at this point, I haven't expanded anything yet. My min heap just says, at this point, I'm at this node here, and it costs me 0. Okay, so now I say, okay, so while PQ, so while there are nodes in, while there are edges to explore in my thing, I'm going to say current time and node is equal to, I'm going to pop the top node, right? So whatever edge happens to be loaded right on top, that's the one I'm going to pop. And I'm going to set current. As remember, when you pop something, it removes it from the data structure and returns it, does those 2 things. So I'm going to set my current time and my node to be that. So, and then remember, I'm keeping track of the current sort of shortest path to this thing, right? My distance here. So I'm keeping track of this. So I'm saying if my current time, because now I have a path to get to this node, right? I don't know if I had a path previously. Maybe I did, maybe I didn't. If I don't, so if this current time is greater than my current shortest cumulative time, then continue, right? There's no point in looking further. This node, this edge happens to be more expensive just by itself. So there's no value in looking at this. So I automatically continue, right? If, however, it's not, then I'm going to say, okay, so now I'm going to look and I'm going to say, so remember my little, I have sort of my current graph and node. So sorry, I need to remember the logic on this. New time equals current time plus W. Okay, so yeah, so what I've sort of popped here is, so this is new, let me try to remember the logic for this. Okay, so I currently, okay, so for all, yeah, sorry. So for my graph node, if for all of these where I'm sort of keeping my sort of best time, and why am I pulling both of these out of there? Because I'm getting the cost from here. So I have to remember the precise logic of this because I'm pulling out for graph of node, right? Time equals new time. Yep. Okay. Push new time beginning. Okay. Okay. What I'm returning here. So okay. So what I do know is I feel like this is a syntax error, but maybe I'm wrong. But well, anyway, so you may remember, I just extracted right here that I have a potential new node and a potential current time, right? And so basically what I'm going to sort of say is I'm going to say if the current, so I'm extracting, I think this is pulling the index and the current best time is what I think this is pulling, I think, if I remember correctly. Because I'm basically saying that for this node, and the current best time from this node, if the new time is less than Oh, sorry, new time is equal to current time plus W, right? Because when I pop this node here, the top of my min heap, I basically said, so like looking at this thing. So I'm saying here, my current, so this is a good example where I override it right here. Because first, let me see here. So first when I first open this up, let's say I for whatever reason, I traversed this actually the wrong way, but I went 6. So this is 10. So my current best time is 10. But then I have this new edge here that's a 3. And so I'm going to pop this. I'm going to say 3 to this edge. And I'm going to say, okay, currently, so the new time is equal to whatever the current best time is, right? Whatever the current time is, right? That is the current edge that I'm looking at right now, plus the cumulative time to get to this point. So whatever the previous time was. So if this new time is less than the current best time, so right now, because right now I have best time, but if my sort of current time is better than this, then I'm going to replace it. I'm going to basically say, looking at this, right? If previously my best time was 10, but my new time, which is 5 plus 3, is going to be less, is going to be 8. Then I pop that and I say, okay, this is my new shortest distance to this, basically. So I update the distance. Sorry. I update my little distance thing for this index, this new index, to be this new time. And critically, I'm now going to add, now that I've traversed to this thing, I'm going to now add this to my heap. So I'm going to say, now that I've traversed this, I'm going to say, okay, for my new thing, I'm going to take my new time and my new sort of thing, I'm going to throw it into the heap. And so that's sort of where sort of the heap goes. So, and I kind of butchered the explanation for this, and I apologize for that. But that's sort of the basic idea of the min heap. You're essentially saying you're always choosing whatever edge happens to be the shortest, and then you're adding it to the best. Sort of you're taking, okay, whatever the current shortest path is to this node, plus this, and you're comparing it to your existing shortest. If it is not shorter, then don't bother, right? Just continue. But if it is, update the distance to be that, and then push that into the min heap. And say, okay, well, this is the new short path. Push that in here and expand these out and see what's there. So in that way, you're basically sort of, as you're every sort of path you're doing, you're always cumulatively building out the shortest path. So you're sort of adding it greedily towards it. And you're always choosing the path by always, because remember, the cool thing about the min heap, and this is sort of part of how you prove correctness, you're only ever looking at the shortest edge you have available to you. And you're only adding it to your path if the cumulative cost of using that edge is less than your previously calculated cost. If it isn't, then you don't do anything. If it is, you add it, you update the cost, and then you you push all those new edges into your min heap as potential candidates. And then it evaluates those, right? And then it says, like, if I end up going down this route, I say, oh, well, this is the new short path, then all the edges that it could reach, I now then toss into the min heap. It then automatically sorts them for me, and then it reevaluates whatever the shortest one is based on that. So it does that, and then keeps cycling through until it's done, right? So this is while PG, which means while you have active things here, you haven't popped everything. So you keep doing it. Once you're done, then this becomes sort of a little tricky thing. You just return whatever the max is here. So because remember, going back to this, we said, what is the minimum time to traverse? Well, it's whatever the maximum cost is here, right? In this case, it's 8 because it took a total of 8 to get to here. Well, that means it took only 4 to get here, 5 to get here, 7 to get here, 8 to get here. So whatever the max value is, that is the minimum cost that it takes to traverse the entire graph.
I don't know why it's giving me a brain cramp.
No, because I'm using max and min, and it's 830. Yeah. So the maximum value is the minimum of the overall graph. So the way of thinking about this is the original question is what is the minimum time it's going to take for every node to be visited? So basically you're saying, okay, if every node needs to be visited, just find the node that took the longest to get to, i.e. the max, and that's the minimum total time for the entire network. Yeah. Yeah, so it's tricky. And by the way here, and then we add some logic here because remember there's a thing that says max time equals infinite. So that means, because remember we started with default setting for them to be infinite. So what's going to be a circumstance is if that these remain infinite would be if they never get traversed, right? Because remember, we only do the update if we're able to traverse to it because our heap is only checking things to that. So what that means is if that doesn't work, then that means this is a disconnected graph. We cannot traverse the entire graph, which means based on the prompt, we return -1. Else we return whatever the max time is.
Wait, return -1?
Yeah, so that was part of the prompt.
Yeah.
So you'll see here, you see it says, if it is impossible for all the end nodes to receive the signal, return -1.
Gotcha.
So that was a nice way algorithmically of being like, yeah, if we never update it, then that means our graph never reached it. And so that's why it
Really cool.
right?
Wow, that's super cool.
Right. It's super, yeah, like I said, it's super cool. And again, and this is why sort of heaps go hand in hand with Dijkstra, because yeah. Because again, I think what's cool about again the min heap is it always, because in this case you're tracking, where is my oh, did I not keep it? Well, with the min heap, because you're always tracking the minimum edge that you haven't traversed. So you're always, right? So you're always adding, again, greedily, right? The strategy is always take the lowest cost edge you have available to you and seeing if that reduces the total cost.
It's probably my eight month brain, but
Why what?
What's the purpose of finding the shortest path?
Good question. I mean, there's any number of reasons, but like, think Google Maps. You want to go home, find the shortest path. Yeah, I mean, so there's a lot of network optimization problems and things like that. But yeah, I mean, it can be distance, it can be cost, it can be sufficiency, time. Yeah, it's an optimization problem basically, and there's a lot of things like these. You'll see there's other things like minimum span trees. That's like what is the minimum number of edges you need to completely cover an entire graph, and there's there's a lot of optimization problems like that, and again, oftentimes with these algorithms things, a lot of it is like figuring out like when you take an algorithms course, a lot of times it's like you're given a word problem and it's like, oh, you realize actually this is a case of Dijkstra, or this is a case of one of these other things. And it's like fitting that in. Like reading this, Google hires you to plot destinations and optimize it. Like, oh, that's just Dijkstra's. And then, yeah. So. Whew, okay, sorry guys. I butchered the explanation for this a little bit, and okay,
It's all good. We're working through it all the time. It's all good.
but yeah, I think we made the right choice of not trying to type that out.
Yeah, big time. What does Dijkstra stand for?
It's a person.
Huh?
It's a person.
It's a person.
You get to. It's Mr. Dr. Dijkstra. He invented it, so he got to slap his name on it. Yeah.
It's used for.
But no, there are a handful of algorithms. I think Prims is another one. There's a Dr. Prim, and then Kruskals is another one, and yeah, so yeah, nowadays you don't really get to slap your names on things. There was a time in computer science when you could just like invent an algorithm and be like, this is mine, and you got to name it. You had naming rights. So. All right, crew. I
was thinking Lenny Dykstra, the baseball player.
Is there a baseball player? Oh, speaking
Yeah.
of, how's the game going?
Dodgers lost.
Oh no.
Oof.
Yeah. Otani got pulled, 4 earned runs, and no hits.
Well, we've got ourselves a series, no question about that. Yeah, look at that. Who knows, man? We might go 7. All right, I'm gonna stop the recording.